Good morning. In the course PH8251 Material Science, today we will discuss Unit 2 Ferrous Alloys. In particular, we will discuss the topic iron-carbon system, eutectoid steel, hypo-eutectoid steel and hyper-eutectoid steel. At the end of the lecture, a student will be able to elaborately describe the iron-carbon system, draw and explain the various regions in a Fe3C phase diagram, define a eutectoid steel, explain the eutectoid reaction and microstructure evolution in a eutectoid steel with the help of phase diagram, differentiate between hypo and hyper-eutectoid steel, and also explain the microstructure evolution based on phase diagram. Iron-carbon system. Iron-carbon system is a solid solution with limited solubility, interstitial solid solution. This is because iron exhibits either a body-centered cubic BCC structure or a face-centered cubic FCC structure. The carbon atom sits in the voids in the crystal structure of iron. Hence the name interstitial solid solution. The limit of solubility of carbon in iron is 6.67 weight percent. At 6.67 weight percent, the iron carbon system is called a cementite. It is an intermetallic which is also known as the stoichiometric product. Iron with less than 2% carbon is called as steel. Steels are further classified into mild steel, medium carbon steel and high carbon steel based on the composition of carbon in it. Cast iron are iron carbon solutions with more than 2 weight percent carbon. Cast iron is usually used to make utensils, while steel is an engineering material which has wide range of applications in the fields of manufacturing and metallurgy. Hence, we will concentrate about the study of steels. This is the Fe3C phase diagram. Depending on the solubility of carbon, there are various phases like delta ferrite formed at 1535 degrees Celsius, the melting point of iron. When iron is cooled below 1535 degrees Celsius, delta ferrite is formed. It has a limit of solubility of 0.09 weight percent carbon. It is a BCC structure, that is body centered cubic structure with carbon as an interstitial solute. This line at 1493 degrees Celsius, the horizontal line here in this region of the phase diagram, is known as a peritectic line, because across the line at 1493 degrees Celsius at a composition of 0.2 weight percent carbon, a combination of liquid and delta phase is transformed into austenite phase. That is, a peritectic reaction happens. That's why this line is known as peritectic line and the composition 0.2 weight% is known as the peritectic composition, corresponding to a temperature of 1493 degrees centigrade. At 1410 degrees centigrade, pure iron forms a FCC structure called austenite. Austenite, popularly denoted as gamma phase, is FCC iron, and the limit of solubility of the austenite phase is 2.11 weight% carbon. This horizontal line across which a liquid phase is transformed into a combination of austenite and cementite is known as the eutectic line. The eutectic line lies at 1150 degrees centigrade and the eutectic point corresponds to a composition of 4.3 weight% carbon. All these occurs at very high temperature. Pure iron transforms into a low temperature BCC structure called alpha phase at 910 degrees centigrade. This alpha ferrite has a limit of solid solubility of 0.02 weight% carbon. The horizontal line over here, where the gamma phase transforms into a combination of alpha and cementite, is known as the eutectoid line, and the corresponding composition of the eutectoid reaction is called the eutectoid composition 0.8 weight%. The cementite, as I told you, is a stoichiometric product of the iron-carbon system which has maximum solubility of carbon in iron, which is 6.67 weight%. Hope the iron-carbon system has been clearly explained using the phase diagram. You have four forms of iron-carbon alloys. One is the delta ferrite, which exists between 1410 to 1535 degree centigrade. It is a BCC structure at high temperatures with a limit of solubility of 0.09 weight% carbon. Then the austenite phase, for pure iron, it exists between 1410 degrees Celsius to 910 degrees Celsius with a solubility limit of carbon set at 2 weight%. Then the alpha ferrite, which is low temperature BCC structure existing between 910 degrees Celsius to room temperatures, and it has a limit of solubility of, shown here, limit of solubility of 0.02 weight% carbon. Finally, the cementite, which is a stoichiometric product which runs as a straight line here. The phase is a single line shown here at 6.67 weight% of carbon. The circle here, the dark circle here, shows that today's focus will be in this region of the Fe3C phase diagram. This portion corresponds to the eutectoid composition and the eutectoid reaction, with this horizontal line being the eutectoid line. So let us turn our focus to this region alone. Before that, a short recapitulation of whatever we have seen. On solidification, iron forms a BCC structure at the melting point 1535 degrees Celsius. Below this melting point, you have delta ferrite, that is the body centered cubic structure formed at higher temperatures. There is a peritectic line at 1493 degrees Celsius with the peritectic composition being 0.2 weight% carbon. Recall that peritectic reaction is where a combination of liquid and delta phase transforms into an austenite phase. On further cooling, pure iron transforms to FCC structure called austenite or gamma phase. This happens at 1410 degree Celsius. There is a eutectic line at 1150 degrees Celsius where the liquid phase transforms into simultaneously forming two solid phases, the austenite and cementite. This happens at the alloy composition of 4.3 weight % carbon. On further cooling to 910 degrees centigrade, a BCC structure is formed at lower temperature. This is called the alpha ferrite. And at 725 degrees Celsius, there is again a line, a eutectoid line, where 0.8 weight % carbon transforms from austenite phase to a combination of alpha ferrite and cementite. So, our focus would be, as I told you in this graph, our focus would be in this region, and the alloy corresponding to this eutectoid point is known as the eutectoid alloy or eutectoid steel. Hence, we are classifying steels as eutectoid steel, hypo-eutectoid steel and hyper-eutectoid steel. Eutectoid alloy is one which has 0.8 weight % carbon. Lesser than 0.8 weight % carbon, the alloys are named as hypo-eutectoid alloys, and greater than 0.8 weight % carbon, the alloys are called hyper-eutectoid alloys. So, this is the portion of the curve that was marked by a dark circle in the Fe3C phase diagram. Area of interest, that is the eutectoid line. Hence, this phase diagram is known as the eutectoid steel phase diagram. And here you can see that there are three phases existing. One is the alpha phase, another is the gamma phase, and the cementite phase lies at 6.67, but since it is a straight line, you are having the two phase regions, gamma plus austenite plus cementite, alpha ferrite plus cementite, and alpha ferrite plus austenite. So the boundary separating alpha ferrite and austenite from pure austenite is called the A3 line. A3 line is the upper critical temperature line for a hypo-eutectoid steel. ACM is the upper critical temperature line for a hyper-eutectoid steel. It separates austenite phase from the two-phase region austenite plus cementite. The horizontal line in this phase diagram, the A1 line, is known as the eutectoid line. It is at 725 degrees Celsius and the eutectoid composition is at 0.8 weight % carbon. At 0.8 weight % carbon, when austenite is cooled below 725 degrees Celsius, austenite transforms into a combination of alpha ferrite and cementite. Remember, austenite has a carbon content equal to the alloy composition, 0.8 weight %, whereas alpha ferrite has, by tie-line rule, you can find that the limit of solubility of alpha ferrite is 0.02, and so alpha ferrite should have 0.02 weight % carbon, whereas Fe3C has a composition of 6.67 weight %. So you can see the stark difference in the composition of carbon in iron. To achieve this difference, there should be diffusion of carbon atoms. So during the eutectoid reaction, not only does the austenite phase transform into alpha ferrite and cementite, there is also diffusion that is happening to achieve this. So eutectoid reaction is one in which austenite transforms into a combination of alpha ferrite and Fe3C. This reaction is pictorially represented here. It is a portion of the phase diagram of eutectoid steel. It is actually this portion that has been represented here pictorially to identify the eutectoid reaction, where gamma phase transforms into alpha plus cementite. So eutectoid steel is 0.8 weight% carbon steel. At eutectoid temperature, austenite transforms into, so there is a special way in which the transformation takes place. A lamellar structure of alternate plates of alpha ferrite and cementite is formed. This structure is known as pearlite. So austenite transforms to pearlite during a eutectoid reaction. The horizontal at eutectoid temperature, which is known as the eutectoid line A1, which is its conventional notation, is called the lower critical temperature line. Below A1, the austenite is transformed into pearlite. The other two phase boundaries, A3, as I told earlier, is the upper critical temperature line for a hypo-eutectoid steel, while ACM is the upper critical temperature line for hyper-eutectoid steel. For temperatures and compositions above these boundaries, only the austenite phase will provide, hence the name critical temperature. This is the microstructure evolution of eutectoid steel. As you can see, above 725 degrees centigrade, 0.8 weight% carbon in iron exists in an FCC structure, but it is a polycrystalline FCC structure, and hence this diagram shows you polycrystalline austenite phase when the temperature is well above 725 degrees centigrade. The temperature has crossed 725 degrees centigrade, that is austenite is cooled. Austenite, particularly 0.8 weight% austenite, that is eutectoid steel, is cooled below the eutectoid point. Then, as we pointed out earlier, pearlite, that is a lamellar structure of alternate plates of the dark regions denote alpha, while the white regions denote cementite. The alternate plate-like structure, a lamellar structure so formed, is given the name pearlite. It's a combination of alpha plus Fe3C with this morphology. As we saw earlier, steels with less than 0.8 weight% carbon are called hypo-eutectoid steels. When a hypo-eutectoid steel is cooled, say we will now go to this diagram to understand this better. Hypo-eutectoid steels are steels with less than 0.8 weight% carbon. This is the eutectoid point. So any alloy between 0.02 and 0.8 weight% carbon is a hypo-eutectoid steel. So So the hypo-eutectoid steel, we are choosing some random, say 0.4 weight percent carbon alloy. It is a hypo-eutectoid steel. In the region well above the A3 line, that is the upper critical temperature line, it exists in a polycrystalline austenite phase. On touching the upper critical temperature line, the A3 line, there is nucleation of pro-eutectoid alpha phase, particularly along the grain boundaries. The pro-eutectoid alpha phase is such that, here recall the lever rule, a horizontal line is constructed. A horizontal line is constructed and there is the C alpha, that is composition of alpha phase, evolves along this boundary, whereas the composition of austenite phase evolves along the A3 line. And once the eutectoid line, the A1 line is reached, then pro-eutectoid alpha formation is along grain boundaries and austenite has the eutectoid composition now, that is 0.8 weight percent carbon. Hence, on further cooling, what happens? The remaining austenite undergoes a eutectoid reaction to form pearlite. So the end product attained by cooling a hypo-eutectoid steel from pure austenite phase to well below the eutectoid line A1 is a combination of pro-eutectoid alpha and pearlite. So you must understand the dynamics of this reaction so that you appreciate the importance of the phase diagram. So as a hypo-eutectoid steel cools, the austenite begins to transform into pro-eutectoid alpha, as we have seen in the phase diagram. And this happens when it is cooled to the critical temperature line A3. On intersecting the critical temperature line A3, nucleation of pro-eutectoid alpha phase begins. And as I pointed out earlier, the composition of the alpha phase evolves along the solvus between alpha phase and the two-phase region alpha plus gamma, whereas the evolution of the composition of austenite is along the A3 line till the eutectoid horizontal A1 is reached. Once the cooling reaches the A1 line, that is the eutectoid line, the remaining austenite undergoes eutectoid reaction to be transformed into pearlite. So you must understand the dynamics behind this microstructure evolution. Though it is a hypo-eutectoid steel, on cooling below the upper critical temperature, the gamma phase evolves along the A3 line till the eutectoid composition is reached here. So whatever austenite remains at this point after formation of pro-eutectoid alpha along the grain boundaries has a eutectoid composition and it undergoes a eutectoid reaction to form pearlite. You must understand and appreciate how this phase diagram helps us in understanding the microstructure that evolves while cooling a hypo-eutectoid steel. Microconstituents of a hypo-eutectoid steel are combination of pro-eutectoid alpha and pearlite. Pearlite is nothing but a lamellar mixture of alpha and cementite. Hope you understand this phase diagram and the dynamics of how the microconstituents is perlite and pro-eutectoid alpha. In a hyper-eutectoid steel, which are steels with composition more than 0.8 weight% carbon, you can try drawing a similar diagram. Instead of alpha phase, if you have a pro-eutectoid cementite phase will be formed for a hyper-eutectoid steel. So instead of alpha phase, you will have formation of pro-eutectoid cementite, and it happens once the nucleation will happen once the cooling curve touches the upper critical temperature line for hyper-eutectoid steel ACM, and the gamma phase composition would evolve along this line. Again, once the A1 line, the eutectoid line is reached, whatever gamma remains will have a whatever austenite phase is remaining, just like this, similar to this, only instead of alpha you will have a pro-eutectoid cementite formed along the grain boundaries. Whatever austenite remains will have a eutectoid composition, and hence it will undergo eutectoid reaction to be transformed into perlite. So in case of a hyper-eutectoid steel, the microconstituents would be pro-eutectoid cementite plus perlite, which is a lamellar mixture of alpha and Fe3C. As an exercise, I would advise you to draw the microstructure evolution for a hyper-eutectoid steel. Just like the microstructure evolution shown here, I advise you to practice drawing the microstructure evolution of hyper-eutectoid steel. We have come to the end of the discussion today. At the end of this session, I hope you have understood the iron carbon system, the Fe3C phase diagram and the various regions in it. What is an eutectoid steel? How does the eutectoid reaction occur in a eutectoid phase diagram? And how does the microconstituent evolve in a eutectoid reaction? You must also be able to differentiate between hypo-eutectoid steel and hyper-eutectoid steel, and also explain their microstructure evolution based on the phase diagrams. This is a question that has been oft repeated in the university exams. Distinguish between hypo and hyper-eutectoid steels. Describe in detail the different microstructures of slowly cooled steels. So it carries a full 16 mark. So I thought I would give you this rubric based on which you can answer the question. There may be 2 marks allotted for identifying the differences between the eutectoid, hypo-eutectoid and hyper-eutectoid steels. Then you would be expected to write the eutectoid reaction and explain the microstructure evolution of eutectoid steel with the help of a neat phase diagram and the microconstituents represented diagrammatically. A similar approach is required for hypo-eutectoid steel and hyper-eutectoid steel, which each carries 5 marks. So I would like to assign you with the task of writing an assignment based on this rubric. If this question comes for your end semester examination, I hope you will answer in a clear manner. You can look up at the E-content. You can practice with the E-content that is available to you. All the best. Thank you.